Okay, so let's talk about how to solve this thing. And there's three key parts. Yeah?
Where does the first equation on the last board came from? So you substitute everything on that equation?
Here? Yeah, so basically I got that one equation. I substituted u and v here, what the stream function was, and then I just added the diffusion term. Yeah, I just added it. Yeah. Otherwise, it's all there. So now let's talk about the key components of this thing. And we're going to spend most of the rest of this, a lot of time in the next few quarters being motivated by how would I actually solve this equation. And if you can solve this equation, and here's what's also nice about this, by the way. This is very important. Part of my objective is to give you homeworks and codes that are not easy. I mean that in a way of saying, if I gave you really, let me tell you why I'm doing this. We've had a lot of numerical courses in our department for a long time. And what you learn how to do is solve the simplest problems. Here's how it works. And you think you know how to solve it. Then you get to a research problem. And you just don't know how to make the jump. Because you've solved such simple problems, you've never encountered a difficulty in your life computationally because we were doing stupid textbook problems. My objective is to prepare you to do research in this. If you can solve that problem, you can pretty much kick some on anything. Okay? That is the objective. It costs you a little bit more. It's a little bit harder. At the end of the day, though, the kind of things you deal with in solving a realistic problem like this get you ready to actually solve a real problem. I am not interested in teaching you how to solve a toy problem so that you come out of here not knowing how to do anything in real life. Okay? There we go. So understand that in the homework, like even your first one, there are questions like, well, oh, how do you actually, oh, that's kind of interesting. How do you handle every single problem you're going to encounter in your research life is always going to have one issue there that you're going to have to figure out. How do I deal with that? Because if you don't have to deal with that, probably somebody already did it. Okay? So just, there's my little soapbox. Do you see the soap? Oh, shiny it up. Okay, there we go. So this is what we're going to solve, and let's talk about how we want to do it. There's all kinds of these parts that we've got to do with this. So first of all, I have some, there's different parts of this. Let's look at this. When I look at this piece here, this is what's called, we have three types of PDEs in general in life. You know, PDEs are just simply time-space dynamics. This PDE is called hyperbolic. And what it generates are waves. Wave dynamics gets generated by this set of equations here. Okay? And in particular, nonlinear waves get generated by this equation. Now, you may think, well, big deal. Nonlinear waves can create shocks. Shocks are kind of discontinuities. They're like these rapid changes in your solution, for instance. Okay, and shocks are very difficult to handle numerically. Okay, so you've got to understand how to do wave propagation. You also have in this problem this piece. This is called the parabolic equation. And this is diffusion processes. And oftentimes, the strategy you'd use to solve a wave problem is very different than what you'd use to do a diffusion problem. This is a problem where things diffuse away. You lose energy in the system. This one's not losing any energy. These are just waves flying around. This loses energy, and you have to think about how to handle that. And then finally, this one here is an elliptic problem. There is no time. It is simply a Laplacian equal to omega. This is Poisson's equation. You have to solve it. This is a giant AX equal to B problem. And I'm telling you right now, you may think, oh, that looks hard. There's your bottleneck. That thing is your number one deterrent for solving fast code. Because this thing here, there's no time, but every single time you take a step in time, in fact, we're going to talk about this. And let me end, in fact, what we'll do is I will talk about this, obviously, more on Wednesday. But one of the things you think about is I want to step forward in time, so I've got to think about how to do that. And by the way, how do I step forward in time? You already know how. We already know how to do this. We have something like OD45 sitting there telling us how to step forward into the future. We have to figure out how to handle derivatives. No problem. We'll do that next time in class. But once I get the derivatives figured out, and remember, ultimately what derivatives are, it's about relying on your neighbors. Derivatives are about saying, hey, I need to calculate an x derivative here. Well, that's just a slope. So how about if I use my neighbors to give me a slope approximation? So what you're going to do is you're going to set this problem up, and at every point, you talk to your neighbors to determine your derivative so you can move forward into the future. Okay? And then this one here, that's a giant ax equal to b. And when I mean giant, oftentimes we're going to be doing 10,000 by 10,000 matrices here. Okay? This is the biggest bottleneck in computation. You've got to solve that. Okay? All right. And so we want to march forward in time, and every time we march forward in time, we have to update our stream function. So you start off with an initial vorticity and an initial stream function. Or actually, you can just start off with an initial vorticity. You say, give me a snapshot of what the vorticity looks like at time 0. And you say, okay, I have it. Now, from time 0, I want to go delta t into the future. Okay, so you know how to do that with an OD45. You know how to take a step forward. So you do that. But, oh, wait a minute. You need to know the stream function. So the first thing you got to do is, once you have the initial vorticity, you got to say, I need to calculate the initial stream function. So you go solve this ax equals b problem. Costly for you. Once you get it, then you can take a step forward in time. Now you have the self-solution delta t into the future. Now you say, okay, now I'm going to take another step into the future. But before you do that, you got to go recalculate the new stream function to the new omega. You have to keep doing this over and over and over and over and over and over forever. Okay? So this is the important hold-up for you.
So the elliptic being calculated every time, but are the hyperbolic and parabolic just special cases of this? And the full model, you don't solve those two separately?
No, and I put them all together. So I said that I separate them here just to show you there's very different physics going on, and actually that does make a difference in computational schemes. But ultimately, we're just going to solve this here all together. And by doing this, we're going to get this nice evolution dynamics, show some vorticity dynamics. You'll make really cool movies. That's what I'm all after, is just cool movies. Cool color schemes, show them colliding and stuff. Really sweet stuff.